Okay, I'll wait a minute or two for anybody else to show up. This is good academic habit. Everybody's going to be a few minutes late.
If it makes you feel better, most people here don't come to work until about like 10 a.m.
They don't have small kids. So that's okay. It's everybody sort of gravitates to their own pattern. How are you?
Good.
Yeah. They found you an office, or is that
It's a phone booth type of room because all of the offices are shared. So whenever someone has a Zoom meeting, we come in like the more private room.
cool? All right, awesome. Yeah, I'm just gonna. I don't know. I just feel weird in these initial things. I'll just see if I can clip it off. Yeah, so happy to see that you're enjoying your New York. That is excellent. New glasses.
It's incredible.
Okay, good. Are you doing fun stuff? Because New York is opening back up, right? So.
Oh, it's all kinds. I said there's like I think like 75 of the population is like vaccinated. Like they're having like pop-up shops for anybody now, and they're having the point to where like nobody's going because everyone's vaccinated.
Nice.
So it's really nice. Like most of the CCA is like it's totally flexible on like masks because everyone here is required to be vaccinated. They also made announcement that they're buying lunch and dinner every day, Monday through Friday. So that's nice. Plus free coffee, free snacks.
Nice. You're in research heaven.
Pretty much.
That's awesome. Fantastic. Yeah, this is exactly what I was hoping it would be. And I don't know, a month ago that didn't feel like that was going to happen. So I'm stoked for you. Do you have a good fun group of people to work there, or is it the other summer students?
There's students, but it's mostly all grad students. So I'm definitely the youngest, at least that I've seen in the building, but like it's also fun. Everyone is super friendly. Everyone's always like, oh, let's go out to dinner. Like it's a lot of fun, and it's really nice. Like I absolutely love it. Like Blakesley has her own group of students, and we meet once a week for meetings. We have like coding hour once a week where we all get together and share our frustrations with our coding, and we have writing hour. So like we all get together and work on our papers. It's fantastic. It's going to be so hard to go back to Kentucky.
Well, we'll see about how you can get you to do grad school in New York, or maybe with Blakesley. So we'll see how we do that. Yeah, you're giving me some ideas. Like writing hour and coding hour sound really useful. So maybe we should adopt some of those things, right? So I've been thinking about how to do group meetings and how to do group things. I like the one-on-one interactions because that helps, but all right. Do I start at like 5 past and just start and see how that goes? Because the last time I did that, I had to admit everybody while I was talking, and that doesn't help either. So anyway.
I mean, yeah, I think that's okay.
It's I'm gonna wait just a little longer, and then it's go time, and then I need to clip our conversation off so that I have to make sure that all the chat gets clipped. There's the CCA did a really great online conference as well, and I really sort of hope they keep stuff like that going, like because there was discussion over Zoom, but then like everybody recorded their talk, so you could just watch talks at your own pace. And so yeah, it's really nice. I'd like to keep going with that stuff. So cool. Yeah, I saw something about you're updating still our paper as well. You should be working on your paper, right? If you're on your stuff with Blakesley.
We haven't really gotten to like a paper kind of like standpoint, and mostly because like I think like the first like 3 weeks was just this is what like this is what the simulation is, like this is what the code's doing. So it's a really big learning curve so far, just because the content is a little bit above my pay grade. I've never worked with like theoretical astrophysics before. So we were working on that, and just so like I would have something to work on during like writing hour and stuff. They were like, yeah, work on your project, like show us your project. Because everyone's like, yeah, I've been working on this for years, and I wanted to be able to say, yeah, this is what I've done. I'm not like, a total beginner. So
Hey,
that
you're the
was
youngest one
fun.
there. You're the youngest one there.
Hmm.
Don't sell yourself short. You're there.
Hmm.
So that's a hard room to get into. So well done.
Yeah.
Uh, okay. Uh, yeah, don't try to do everything. Don't like that
Hmm.
project will be there for you when you get back. No worries.
Yeah, for
So
sure.
I was thinking about it. I have some fun ideas to like how we could do the next step, and so basically have like a
Hmm.
full project. And so that would be cool to take to see what happens next. But I'm really curious to hear what you're going to do with the fire simulations and what comes out of those and how you can compare. Perhaps that would be really neat. All
Oh, it's
right.
awesome.
I'm going to go kick off because I'm just feeling awkward at this point because I'm like, I was all ready to give a talk, and now, yeah, it feels strange to do it to one person, but I'm just going to go get started if that's okay with you. Yeah.
Awesome.
All right. Cool. Let's see if I can share my screen. Do the usual. Here we go. Here we go. Can you see this?
Looks good.
All right. Play. Okay, so galaxy morphology, the appearance of galaxies, lecture 2, the subgalaxy scale. So last week we talked about the visual morphology and galaxy-wide profiles. So if you just look at a galaxy, you just want to describe how the whole thing looks over the entire galaxy scale. So you sort of approximate and you average out over all the small stuff that you see. And that seems to correlate pretty well with visual morphology as well. So we had the visual morphologies that Hubble and his contemporaries and students in follow-up basically came up with that Hubble tuning fork, and then also the profiles that we use to fit those. And so we have a good description for most galaxies on like a large scale, on the scale of the galaxies themselves. But today I want to talk about just about like everything else. It's a bit of a grab bag of all the other little things that they noticed while they were visually more classifying and while they were trying to do these galaxy-wide profiles. So I sort of made that into one giant basket, but essentially it's things that are about a kiloparsec in scale. That's important because a kiloparsec in scale means that it has a reasonably long, it has a certain time scale as well associated with it. And a kiloparsec is reasonably well identifiable over a large volume of space. If it gets any smaller than that, you can only see it in nearby galaxies. And if it gets any bigger, well, you're sort of at a galaxy-sized thing then. So we talk about bulges, bars, something called ANSI, lenses, rings, and then shells and tidal tails, mostly tidal tails. So those are all the kind of other things that people noted down as they were visually classifying galaxies. So we sort of encountered bulges and bars already because the Hubble tuning fork uses them to classify. And so the bulge is the central blob in the center of a spiral galaxy. That's the bulge. And you sort of, if you look at them, you look at these pictures, you go like, yep, that's a little central concentration of stars, and so that's the bulge, and then you have like this elongated thing, and that's the bar. And so they already featured in our discussion last week. This is the original sketch by Hubble, and you can already see that, yeah, that's sort of how we think about, how we talk about galaxies today. Barred spirals, normal spirals. It's always funny to see things like normal appear in discussions like this, because what's normal? That's sort of a value argument right there. So we have bulges, we have the classical versus the pseudo bulge. So people refined this and looked at their profiles, and they looked at their Sirsic profiles. Remember that from last week. So they looked at the Sirsic profiles of the bulge, of the inner parts of these galaxies. And the classical bulge follows a divocular profile, 1/4. So it looks like a small elliptical galaxy. It's almost like a small elliptical galaxy plus disk. And so that kind of tells us something about how these things formed. So we think they originate from very early interactions. So the bulge formed really, really early in the universe, and sort of as one monolithic collapse, or like a lot of quick interactions with very small components. And so you end up with a elliptical galaxy, a small elliptical galaxy that then accreted a disk around itself. Pseudo bulges, they sort of follow a cyclic profile that's much closer to a disk. So think of an index of 1.5 or 2 or something. And so they peek out of the out of the disk of a galaxy, but they're not an R a quarter NS4 kind of profile. They are, flatter. And some is even, so this is the thing that we can now start seeing with something called an integral field unit. We can see that these things rotate. And so bulges are supposed to just have random motions, right? So if you have a blob of stars, they should have every orientation of orbit that you can think of. But if you have the whole thing sort of rotates with the rest of the disk, then that suggests a common origin, where you start with a disk and you sort of puff the center up a little bit, because that's where the stars are the densest, and so they encounter each other the most. And so the gravitational interactions, the heating sort of heats up the center of the disk, and that becomes what looks like a bulge. And so hence the term pseudo bulge, because it's like, yeah, it's not a real bulge, because a real bulge, a classical bulge, it started first and accreted the disk later. Now, this is still being debated, but that's sort of the two kinds of bulges that we kind of see in the universe. There's like classical ones, the ones that must have started early, and the ones that have formed from the disks themselves. Bars, on the other hand, happen when you already have a disk and it sort of starts buckling, and so it's like, kind of like symmetry breaking, where suddenly, instead of having round orbits, all the orbits kind of crash into something that has one high ellipticity bar. And so there's a lively debate on how long these things lasted, and I don't think it's quite over, because as soon as you have a pattern like that, how long does it stick around? And about 35% of all Milky Way kind of disk galaxies have a bar. It depends a little bit on, where you set the bar. So if you think of it like, is this an elongated bulge, or is that a clear bar? And also, of course, how big is the galaxy? So for example, the Large Magellanic Cloud, which is an irregular galaxy, has a bar-like structure. So it does have a bit of a disk and it does have a bar. It just doesn't seem to have a very clear center. Our Milky Way has a small bar that we're looking straight down. So we're actually having a real hard time measuring its length, because we're looking right down the length of it. And so it's a little tricky to see how often these happen, and also, do they form and dissipate? Do they form and dissipate? Is that like a cyclical thing, or is it they form and they stick around, or they form, they dissipate, and that's it? It's a little unclear, but as we look further and further back, we do keep seeing disk galaxies with bars in them, but that's also was a hotly debated topic for a little while. So bars and rings, is there a link to, if you see a ring in a galaxy, if there's like do the bars form rings, for example? So on the left-hand side, you see a barred galaxy with a very clear, nice ring in the around it, and you kind of go, well, that looks, the one knows about the other, or one has, there might be a cause of effect going on here. Except that if you have then a really strong bar in the right galaxy, and there is no ring at all, apparently a bar does not necessarily mean that you're going to form a ring, or maybe it takes a little while to form a ring. So bars and rings seem to be related, but that doesn't mean that they're always can be found, or exactly what is the cause and effect. So one more thing that we notice with bars is that sometimes at the end, there's a little bit of a bright spot, and that bright spot sometimes elongates a little bit. So you can see that here, there's these two slightly brighter blobs at the end of the bar. Sometimes they're yellow, meaning older stars, and sometimes they're blue, meaning fresh star formation. And so, are these the start of arms, or the ring, or is this a ring getting started? So those are called the ANSI. And so that's another little note on, as we morphologically classify galaxies, we noted things like ANSI. And so as you go through these things, all these galaxies, you suddenly start having these really complicated set of notes on basically all of them, where in some cases you see an inner ring, an outer ring, it's circular, it's not quite closed, but it does look like a ring. There's a bar, there's ANSI. And so how are these all linked together? And then we kept finding more rings, and this is an example from as you do photometry and you subtract all your disk and your bulge, and then you're still left with a little bit of light that you need to explain. And so sometimes you have these rings very much in the centers of galaxies. So they're not at the end of bars, they're basically inside bars or inside bulges. And so what exactly is happening here? And so that could be, there are clearly many different mechanisms to form rings of stars and rings of star formation in galaxies. And so the origin can be tidal, it can be a shock wave of star formation, it could be resonances, and we'll talk about resonance soon. But people talk about inner, outer, and nuclear rings. So rings that are really close to the center and sort of seem to orbit are inside the bulge or a part of the bulge. Then you have outer, that's sort of on the outside of things like bars, inner, that's closer in. And so you have these different differentiations between different morphologies, but they're all rings. And so they all might have something to do with how disks form and how disks evolve over time. Okay, so we have a perturber. And so disks are not smooth, despite the fact that we have this lovely exponential profile or this lovely Sirsic profile that we fit to it. There are lumps in there. There's spiral arms, there's spiral structure, there's bars, they're not completely axisymmetric. It's not a perfect hubcap. And so those lumps actually exert their own gravitation. And so as they orbit around the center of the galaxy, they start resonating with other parts of the disk. And so those resonances make sense as a mechanism to start building rings. For example, if you have those resonances, you have essentially omega beta here is the perturber. So it is whatever asymmetry feature there is in the disk, something like a spiral arm, something it's like whatever is the deviation from the smooth disk. And that orbits, that pattern orbits with a certain rate. And so you think about bar pattern speed or spiral arm speed. So that pattern moves in the disk. The whole disk can move at a different speed, but that's the part that we're interested in. And then we look at somewhere else in the disk where there's a star orbiting with a rotation velocity of omega. And so if you have these integral numbers of orbits, or if you get these resonances now, then they talk about epicyclic frequency, and that's kappa. So what you get is that you have a bar, and it's supposed to keep rotating, and as it hits you can sort of see that it's in a certain resonance here, and so plop, there it is. It kind of gets a little jerk every time it is aligned with the bar. And so if you're not exactly aligned with the bar, you also get that jerk. So either your orbit gets sped up or you get moved on a radius so that you are in fact in resonance with the bar. So you can see that if a bar keeps rotating in a disk, if it's there long enough, it probably starts establishing a ring on the outskirts in exactly one of those resonances. And so you have these resonances on the inner and the outer parts. And so that's how we end up with inner and outer rings. So you can also just co-rotate, where essentially you're in the pattern or you're completely antipodal to the pattern. And so now it also brings you into lockstep. So you can sort of see how that strengthens things like a spiral arm or strengthens things like a bar. So you have outer limbat resonances where the orbit lags a little bit behind. So basically the rotation is starting to nudge you a little faster. And so you do these, you can have that at particular points, but really the outer limbat resonance is usually what the outer ring corresponds to. And so you can actually start modeling how much mass and how fast that ring must be going, how fast the bar needs to be going. And so you can also do that with where you actually overtake the actual the star overtakes the perturbance, and so then you get a ring, and it's the inner Lindblad resonance, and so it's obviously named after this Swiss chap called Lindblad, and so that explains at least some of the rings that we can see. We can say like, okay, here's the mass, and this is the pattern speed that we're seeing or estimating, and this is that's the rings, and they make sense for us now. However, we also see things like this, which is basically a really small ring in the middle of this huge bar. And so what kind of resonance is that? And so what we think is that actually has nothing to do with the resonance, but it has more to do with the gas flow that we see along the bar. You see those dusty lanes there. And so they hit the orbit of maybe a minor, it's a very tiny nuclear bar. So there's bars within bars, and there's rings within rings, and that also is resonating, and that gas then all piles up in this one ring because there's extra material there, so the gravity kind of traps the gas there, and so the gas accumulates there, density goes up, star formation happens, and we can actually see the ring. So the cool thing is that you get this on multiple scales. It's almost like the Matryoshkas, or it's totals all the way down. It's rings and bars and rings and bars. So it's a very neat and seems to be very good working way to get rings in disk galaxies. But sometimes we see something like this, and that makes no sense because there's no bar. In fact, the inner galaxy is super smooth. It's basically an elliptical. And what's happening here? And so what we think happened here is that there's basically was a burst of star formation, and you get a shock wave, and that shock wave kind of shocked all the gas in a neat little ring, and then you get a ring like this. This is Hoag's object. Another thing that can happen is that you hit a galaxy dead on, and that shock wave ran out, and so there's a beautiful, little old-fashioned, but here we go. The shock wave actually travels outwards. And so you end up with a ring with a little bit of spiral structure going to the ring structure, but that's also a way to get a ring to explain some of the rings that we can see. I love the fact that this is still a pretty good simulation, despite the fact that it's now, I think, 30 years old, but it neatly explains what happened. And in fact, it explains a galaxy like this. You can actually find out that it's the bottom left of the two smaller galaxies you see there that just travels straight through this galaxy and left it looking like this. Now, of course, that's a rare event. That wouldn't explain all the rings that we see. It doesn't explain all the morphologies that we see. So the bars explain most of the rings, and then we have a bunch of rings that can be explained like this, not that many. And then we have a series that are explained by simply a smaller galaxy encounter. And so we have all these different kinds of features within disk galaxies. It all depends on also how well we can see them, because if everything is nice and smooth, if you're basically talking about a red galaxy where there's no new star formation, you kind of see it, and it's an actual difference in contrast. It's an actual difference in the light, and so you can go like, okay, that's an actual concentration of stars in this particular pattern. In the green kind of galaxies, there's also some blue, and the blue is basically new stars. Fresh star formation sort of throws off how well you can trace the underlying stellar mass, because those few young stars are so bright they dominate the light distribution. That doesn't mean it's an actual physical thing. It's just a small ring of fresh star formation. That doesn't mean there's a big mass there. And then in the blue galaxies, it's even harder, because then all those smaller structures are typically dominated by star formation, which means there's gas there, and there's mass there, and there's star formation happening, but is it an actual overdensity? Is it a real difference in the way the stars are distributed in this galaxy? So we have all these different kinds. We have the bars that are rectangular, and so we've got bars and rings here at the top. And bars are these actual rectangular things. Lenses are elliptical, and so it's sometimes hard to see what they are. I mean, I find the top, so let's see, not quite top left, but second from the left, pattern is that's like, yeah, there's a bit of an elliptical shape to it, and then basically it's helped by the fact that there's a dark spot there as well, or darker spot, and so you can see that they're not quite bars, but they're also not quite as round as a bulge, and there's something in between. So is it maybe an intermediate form? It's kind of hard to explain. And so we're also dealing with the fact that our eyes, us humans, are great at pattern recognition and therefore also great at making patterns up. So you sort of want multiple people to agree that's in fact a lens and that's in fact a bar. And so that's another discussion when we talk about the Galaxy Zoo. So tidal features, this is the last kiloparsec scale. Well, it's kiloparsec scale on one scale. They're about kiloparsecs thick. They're multiple kiloparsecs long. And so when you have tides, when two galaxies come closer together, one side is less bound to the galaxy, and the other side, both the edges of the disks start to encounter tidal effect. So you get that they get unbound from the main galaxy. When that happens, they sort of start flying off into the distance, and that's what you see here. And so not only the stars, but also the gas that goes with it gets flung off, and as a result, basically compresses and forms new stars. So they're briefly visible as bright blue things, and then the young stars die, few million years later, and suddenly the whole thing fades. So the reason is that you can see this, and you know that this is not going to last a long time. So if you see this a lot, that means it must be happening. It has a short time scale to exist. So if you see this at all, that tells you something about how often this happens. It must be happening a lot. So that's called a major merger. We'll talk about morphological transformations as well. Again, we're looking at two disk galaxies that are sort of smashing into each other. And the neat thing is that there's this whole Hubble category. This is why I love this particular movie, despite the fact that the simulations are already starting to look a little dated. I love the fact that they ran through this whole simulation and then sort of found the camera angle that goes with the Hubble picture that sort of shows the same thing. So we see these different transitions, and then there they are. There are tidal arms and our tidal features. And so we see these things happen in the sky in like these rare events, or relatively rare events. And these were all the galaxies that sort of ended up in the miscellaneous, in the irregular or peculiar, especially peculiar. There's an Atlas of Peculiar Galaxies by Anton Arp. And essentially, this is a long list of everything that didn't fit in the Hubble tuning fork and also wasn't an irregular shaped galaxy. It was just something really strange is happening here. And part of that is the formation of tidal features, the tidal arms. Now, this is the most dramatic way to get tidal arms. You take two equal mass galaxies and you smash them together, and like half the gas flies off. And so that's a way to do it. But you can also have much gentler interactions, and so they start looking like looking more like this. So this is also an interaction, but not as dramatic. Like they haven't actually smashed into each other. They just sort of skimmed each other. And so they skimmed each other briefly, and I'm going to check real quick if there's anybody else who wants to participate. Nope. Okay. And so they just skimmed each other. And so you end up getting like a spiral arm on steroids. So something like this here, where there's a big swirly thing. And so typically we think if you see a spiral galaxy with one giant spiral arm and no counterpart on the other side, for example, that's a good indication that it got nudged by something. And so it's not so much, it doesn't have to be a catastrophic merger like this. Sometimes you get these small blue features on the outskirts and you go like, I wonder what's happening there. And especially if it's asymmetric, if it happens on one side but not the other, that's a good indication that something sort of skimmed this galaxy. And sometimes you see this as a bridge from one galaxy to the next, and you go like, well, these two are clearly interacting. You also can have a minor merger. Why smash two big galaxies? Because small galaxies are much more common in the universe. So you can have a smaller galaxy that sort of falls into a much bigger. So the much bigger galaxy is sort of completely unperturbed by this. Yet the smaller galaxy is doing what you see here. The tidal effects sort of strip it, put the whole thing into one giant stream. And so you end up with something that looks like a giant loop. We'll talk about these more even in the low surface brightness universe, because that galaxy is not so much starbursting, or these loops don't have much star formation. They are simply whatever remnant of the galaxy you had completely strung out. But they do appear once in a while. Because it's my show, I get to go talk about what some of my favorite galaxies. In this case, that would be M51. M starting for Messier, as you remember from last week. So it looks like a grand design spiral. And it sort of is like the template for this is what a spiral galaxy looks like. There's a little bulge in the middle. There's these beautiful swirling spiral arms. There's symmetry. You see one going this way and the other one going that way. There is, that annoyance satellite galaxy, but other than that, this is how all galaxies, all spiral galaxies look. That was sort of our template. This is always what we go. If you have a new telescope, we typically point it at M51 because it will make a great picture. This is the Hubble picture of M51, where you can see the young stars in the spiral pattern. You can see the dust that will form the next generation of stars. It looks like, this is a good way to understand spiral structure. But as you can speculate, what is that second galaxy, that elliptical galaxy that's sort of behind M51, M51b sometimes? What is that doing there? So if you look at it closer and actually now take the sort of wider view and you look at it deeper and deeper, you see that there's tons of spiral, not just spiral structure, but also tons of tidal structure. And those tidal structures really can only be explained if this actually was a close encounter with that second galaxy. And there's no star formation in these. These are just simply bits of both galaxies that got stripped off. So they're now just made out of older stars, much dimmer, and spread over a very large area. So they're really hard to see. So we'll revisit this in the low surface brightness universe lecture. So I have that, okay, but didn't spiral galaxies have lots of gas? So what does this look like in the gas? Well, in the gas, you also see lots of tidal features, but they don't particularly coincide. So there's a reason that we don't see star formation in these. And these features are so low surface brightness, there's so little gas in them in any given volume that there's not enough to get star formation going. This wasn't a strong enough encounter to, get these blue, strong tidal features. There are tidal features, but they're not perturbed enough to actually be star forming, so we don't see them in the blue, so we don't actually pick up on it unless we stare at this galaxy for a very long time. So there's all kinds of different tidal features around galaxies. Basically, if you start looking at any given large galaxy, there's going to be something. Either it just ate a small galaxy, or it has like a close encounter. This is a 1:3 mass ratio. And if it has, if it's unlucky enough to be near a galaxy that's about the same mass it is, that's a 1:1 ratio, then you get complete deformation of the morphology. But other than that, you can just look at something and go, that looks like a perfectly good spiral galaxy. And then it ends up having all these tidal features as well. So in fact, this was reproduced by n-body simulations. N-body basically meaning I take a computer, you put n-bodies in there. So you put every star, not quite every star, but every pixel is a star, or 100 stars or 1,000 stars, but you model everything as a bunch of things that orbit each other. Gravity is pretty easy to tell a computer how to do, and you integrate over all the masses. And then you have a potential, and then you just have two of those smash into each other. This is now a whole industry, but I quite like Heike and Salo's original paper here, where they got not only that you get this spiral pattern in the main galaxy, but you also get these tidal features around it. So it actually explained all of it. It's all induced by the encounter. Okay, so we had a lot of these visual classifications. why are we doing this? Well, so this is sort of the beginning of how to do science, where you first start to figure out how many of everything there is. And so it, disparagingly, you can call it stamp collecting or butterfly collecting, but honestly, it is something that you need to have before you can even develop an intuition for the kind of physics that's actually driving everything. Because the frequency tells us how often a thing is happening. It also tells us how long, for example, it's visible. I talked about how these these tidal features, if they're blue, we know that those blue things happen. I mean, they're visible for cosmologically a very short amount of time. The entire interaction takes, billions of years, but those young stars form and live for at best 50 million years. So if I see that, that means, and I see it a lot, or I see it at a certain amount, and it's only a short time scale, then it must mean it happens quite often. If I see, if I see these strong interactions with like these huge tidal features where like two galaxies are really smashing into each other, I can figure out how long that takes. Well, it takes about 2 gigayears for them to coalesce into an elliptical galaxy. So is that a viable way to make all the ellipticals I can see, right? So that's the kind of thing, this gives us intuition. If we look at a certain volume, we look at our nearby galaxies out to a certain area, that gives us a nice spherical volume. And if you say, okay, how many mergers happen there? How many mergers are currently going on? We know it takes about 2 gigayears, 2 billion years to happen. So this gives us a merger rate. So this is how often two spiral galaxies smash together. And then from that, we can figure out whether or not this is a really important thing, or like this is how all elliptical galaxies happen, or if it's one of those that is like, yeah, it happens, but it's incredibly rare. So in principle, all of a galaxy's history is in kind of visible in the subtle scars and features of its morphology. And the trick is to actually link these morphologies to how it's been evolving. For example, bars, did they all get their start from like a chance encounter from a flyby from another galaxy, or is that something that happens on its own? And so we need our butterfly collection, we need our stamp collecting, we need our classifications really badly before we even have an idea of what physical processes are important. Because often as not, there's multiple ways to roam. There's multiple ways to make the same or very similar looking features. So I told you about the big spiral arms. You have these grand design spirals, and even if they're symmetric, that could be flyby induced, but they can also be simply something that happens in disks. It's a kind of symmetry breaking. So it is the kind of thing that we need classifications before we can actually start saying what we're looking at. Now, another part is that we can start quantifying the features themselves rather than saying, I see a bar here, or I see an inner disk, and I see a bulge, and etc. We can actually model all these things. So you take the light profile now in a digital image, and you have models for the bulge, which is the Vauquelin profile. You have a disk, which is Plummer profile. There's a couple of descriptions that are not a Searsic profile and basically describe a bar pretty well. And so you can keep adding components. Now, that sounds like a straightforward way to just decompose a galaxy. You can take a galaxy and say, okay, here's my disk, here's a bar, here's a lens, here's a bulge, and so I'll just add them all together, and that describes my entire galaxy, right? So I have in the middle, I have the Muse field of view, so it's a Muse observation, and I model that with all these different components. I've got 1, 2, 3, 4, 5, 6 components, and I add those together, and still in the residual, I'm still seeing a ring. So maybe I need to add one more ring to fit them all. Oddly enough, this is an incredibly degenerate parameter space. And so you can either up the bulge a little bit, and then the disk becomes less important, or the disk becomes so they all react to each other. So your optimal solution often is degenerate, meaning that you can have you can say, well, I have an inner disk and an outer disk, for example, here, or galaxy disk and an inner disk. So if I make my galaxy disk steeper, then I maybe don't need that inner disk anymore. Or if I make that inner disk more important, that galaxy disk gets flatter. Like all those things kind of influence each other. And it's a knotty problem to fit. So this is a fantastic example of all the different morphological components, because then you can say, I'm seeing this many stars in the bulge, I'm seeing this many stars in disks, multiple disks, I see this many stars in bars, and I see this many stars in like a ring. So if I do all those things, then I know how much mass was originally in the bulge, for example. So I know of this entire galaxy, 5% resides in the bulge. And so if I say that was the original galaxy that I started with, like back when the universe formed, that was a little blob that the rest of this galaxy formed around. Like 5%, I know how much stellar mass is in there. So you kind of can look for progenitors in the distant universe, for example. Or you can say, well, I need to actually form the rest of the disk then. And so I need to, whatever model I make for accretion of gas, it actually has to be reasonably physical to build a disk that big. And so it's surprisingly difficult to do this. But we're moving from visual classifications, which are incredibly useful to know, to build intuition and to know the frequencies, to actually quantifying these features and saying there's this much mass, there's this fraction in this particular component. And that's important also because bulges are pressure supported, meaning that the orbits of stars are all over the place. So they're basically like an isothermal blob of stars. And disks are rotation supported, so they are rotating with a certain speed. So if you go from rotation to isothermal, that something has happened, something has rearranged all the angular momentum in these galaxies. So it tells us something about the kinematics and the evolution of the galaxy as well. So within the broad Sirsic profile, there are many, many, many additional features possible, and especially in disk galaxies, there's rings, bars, NC, outer rings, inner rings, nuclear rings, and lenses, and often all these things combined, as hopefully the previous slides showed. And so the combination of these makes each galaxy appearance almost unique. And that's the other part. This makes all spiral galaxies, as long as if you study them long enough, you kind of go like, oh, that's NGC so-and-so. And so you start knowing the numbers because they have their own unique set of features. Every combination is almost unique. They have commonalities, but it's interesting to see, like everybody has a nose, but everybody has a unique nose. And so it started with stamp collecting, but now we're connecting the physics to the morphological phenomena. We're trying to see what is the most common thing to make the thing that we found. Modeling a single image, however, is really complicated. It is still the hardest thing computationally that I've seen people do sometimes, because it has a big parameter space and there's lots and lots of degeneracies. It's a knotty problem to get started on. Funny enough, we're now often modeling these things over multiple images, still different colors, for example, or with different stellar populations. But it is a wide parameter space. And the trickiest part for model fitting is often like, do I need to add another component? So for example, if we're looking at this, we already have 6. Do I need to add a ring as well? Do I? Or do I just, sort of cool it on the disk a little bit and that should be fine? So that's the kind of thing that is really tricky to teach a computer as well, because how many models you need. Every time you add a component, you're adding variables. So central position, strength, size, profile, all these things. And so those are new model parameters. And so you can always add new parameters, but is it valid? And so this is the kind of stuff that until very recently we were very stuck with. But things like Monte Carlo Markov chain are starting to solve the degeneracies, or at least visualize the degeneracies a little better. So we're getting better at this. And that's a good thing, because we're going to get way more of these images. We're going to have to model way more of these galaxies, and preferably in a way that we can just teach a computer how to do it and trust their results. So I'll take any questions if anybody has them. I was hoping for 45 minutes, so we're right on time there. Okay. In that case, I'll talk to everybody next week. I try to keep it to about 45 minutes. If I talk fast, 35, I guess, but try to keep it under an hour. So next week, we'll talk about crowd classification. So we talked about all the different things that we looked at, and these classifications were done by Hubble. These were done by individual people, or possibly, a crowd of all three. And so if all three of them agreed, then it was an SA galaxy. That's sort of how it worked. And so this was the meticulous work over decades of people and on photographic plates to classify all galaxies. And so the thing that I'll talk about next week is something called Galaxy Zoo, where instead of asking, one or two experts, we're actually asking everyone. And so that gives us way more information. It also means that we have to break it down into simple questions so that there's no miscommunication in the questions. And so I'll talk about the Galaxy Zoo results and what you can do with Galaxy Zoo and what you can't do with Galaxy Zoo. That will tie in later with the future of galaxy morphology, because that later we'll now go teach machines how to do it, computers how to do it, but then having crowd classifications will give us a training set for machines to work on, to learn from. So that's how next lecture will go. And that also we saw some previews for lecture 5, low surface brightness universes, and also a little bit of lecture 6. Well, how does morphology evolve? Because I kind of talked about it already. So all this stuff is always cross correlated. All right, I'll talk to everybody next week. Thanks for listening, or online. I'll see you back in the universe somewhere. Bye.
Thank you.
Thanks.